Hi, everybody. Welcome back to Environmental Organic Chemistry with Dr. Lisa. Okay, today we're doing homework number 12, which is about hydrolysis. This is based on problem 13-2 from the textbook with some variations of my own diabolical nature. So the idea here, the question here is, what is the rate constant or the half-life of your chemical in the epilimnion of the lake and also in a hypolimnion of a lake? And the fact that it has an epilimnion and a hypolimnion tells you that this lake is stratified, and that tells you that you're probably in the warm season. And then the question also is, what are the reaction products? So I've decided to use DDT for this example because I like DDT. Here's DDT. And I'm going to answer the last question first. What are the reaction products? The products of DDT, the hydrolysis of DDT is DDE. This is a very, very common reaction, happens all the time. There's a hydrogen here, although it's not drawn, it is there. So there's a hydrogen there, and the nucleophile can come in and pull off that hydrogen. The electrons that were forming the bond to that hydrogen will then swim in here to form the double bond. And in the process, we'll kick out one of these chlorines. And so you get this structure, you get the double bond here. So this is a dehydrohalogenation reaction because you've lost the hydrogen and a halogen. So a dehydrohalogenation reaction, if we're going to draw this correctly, we'd have to say plus H plus Cl minus. Yeah, bite me. Okay. We have to put the little apostrophe here so that Excel doesn't get mad at me. There we go. Okay, so that would be our balanced chemical reaction. All right, so epilimnion, hypolimnion. Here is a picture of a lake from Wikipedia. This is the epilimnion and the hypolimnion. In this picture, they're calling this area the metalimnion, but I'm more used to hearing it called the thermocline because that's where the temperature is changing really rapidly. So in the warm season, the sunlight is heating the water at the top here, and so it becomes warmer. Warmer water is less dense, and therefore it floats on the top, and there's no forces that are driving vertical mixing here, so it just stays at the top. There's a little bit of wind that provides some mixing of the top layer, but it only reaches down so far, and then you get this unmixed layer where the temperature is changing rapidly, and then down here there might be some mixing just due to currents or other things, who knows, maybe there's no mixing, who knows. But this deeper part is going to go anaerobic, so it's colder because there's no heat coming in. It's anaerobic because you can't get the oxygen from the atmosphere to mix down to this deeper layer. The fact that it's anaerobic causes all kinds of microbial action to happen that can lower the pH. So that's why this has not just a lower temperature, but also slightly lower pH. So this condition will prevail until either the lake cools off in the fall, and at that point, once the surface water cools to be the same temperature as the deeper water, then it'll have the same density, and then the whole lake will turn over. Sometimes it's more common that turnover happens when you have like a big rainstorm or something happens to sort of disturb the whole lake, and then you can get the lake to turn over, and it smells bad because all the smelly stuff generated from the anaerobic processes down here gets mixed up to the top and then off gases, and you can smell it. You know that a lake is stratified when you go swimming in it in the summer, and the top is nice and warm, and you lay there on your little floaty raft and you feel terrific. But then when you actually dive into the water, if you go down deep enough, like where your toes are, your head's up here, but your toes are down here, your toes are often down at the thermocline where you can feel it getting cold very fast. Okay, so back to our problem. What are the what is the half-life of your chemical in the epilimnion? This part is relatively easy because the temperature is 25 degrees C. So in the epilimnion, the neutral rate constant is just given right here, 1.9 times 10 to the minus 9 per second. The base rate constant was also given to you, 9.9 times 10 to the minus 3. Note the units, per molar per second, because this is a base catalyzed rate. So to get this into first order units, a pseudo first order process, you need to multiply by the molar concentration of, in this case, hydroxide, because it's a base catalyzed reaction. The base hydroxide is what's catalyzing that reaction. We know that our pH is 8.5, that was given. So 10 to the minus 8.5 is the molarity of the protons, right? Because that's what pH is telling us. It's the minus log of the proton concentration. So to figure out the hydroxide concentration, we need to know the dissociation constant of water at 25 degrees C. That's the number you've memorized, 1 times 10 to the minus 14. Here's the reaction. So it's products over reactants. The activity of water, since water is the solvent, is just taken to be 1. So the products are just, I've drawn it as H3O plus here, but we can just think about it as protons times hydroxide. So H plus times OH minus will give you 10 to the minus 14. So therefore, if you take the 10 to the minus 14 and divide it by the proton concentration, here's your concentration of hydroxide. All right, so then our K, I'm going to put a little apostrophe here, B, because the apostrophe tells me that this is the pseudo first order rate constant, is now this KB, second order, times the concentration of hydroxide here. And so now we have it in units of 1 over second. All right, so lives for the neutral, I can spell neutral mechanism. Here's our calculation of half-life right here, right? So equals natural log of 2 divided by the rate constant here, which is here. And since our units were in 1 over seconds and we've just taken the inverse of it, this now has units of seconds. That might not be a terrifically helpful set of units. I'll move them up here and then we can do this in terms of hours as well. So if we divide this by 60 seconds per minute and 60 minutes per hour, we get still 1 times 10 to the 5th hours. So then let's also multiply that by 24 hours in a day. That would give us days. That's at least a number I can wrap my head around. 4,000 days, so more than 10 years, right? More than 10 years. Certainly don't need those extra decimal places. Okay, for the base catalyzed reaction, again, natural log of 2 divided by our first order rate constant here. The shorter, right? 10 to the 8th here, 10 to the 7th there, so shorter, and I can just copy this down. And now it's only 256 days. So the base catalyzed mechanism is much faster. It's taking less than a year for half of this to hydrolyze by the base catalyzed mechanism, but the neutral mechanism is taking more than 10 years. So faster via the base catalyzed mechanism. Right, so that's the easy part. That was the epilimnion. Now let's talk about the hypolimnion. Hypolimnion. Spelling was never my strong suit. I was always a very good straight A student, except in spelling. Can't spell to save my life. All right, so here's my Kn and my Kb, but now I have to adjust them for temperature, which means I need this equation right here. And I also need to know what my activation energies are. What are the activation energies of these two processes? Well, I actually could look this up. I think there are some literature values out there, but I'm lazy. So for purposes of this homework, I'm just going to guesstimate a value, and this is probably what you're going to do. You're going to have to guesstimate. Guesstimate. This is a technical term, meaning take a wild ass guess. Actually, that's not what it means. It means don't take a wild ass guess, take a guess that's reasonable. So if we go back to the lecture notes on hydrolysis, we had this table. And this table, sorry, that was supposed to help. Instead, it made it worse. Okay, this table is showing you hydrolysis rate constants. Here's the neutral and here's the base catalyzed hydrolysis rate constants for a number of different chemicals, and also giving you the activation energies for some of them. And you notice that the neutral mechanism has activation energy above 100 kilojoules per mole, even here on the second page. Well, a few of them below, but most of them above 100 kilojoules per mole. Whereas the base catalyzed mechanism is a little bit lower. So here it's 6 kilojoules per mole lower, here it's 13 kilojoules per mole lower. So it seems like the base catalyzed rate has a lower activation energy. So I'm just going to guesstimate from here that maybe my neutral E, my activity of my activation energy is about 110 kilojoules per mole, because it's kind of in this neighborhood. And based on this, I'm going to guess that my activation energy Sometimes it's as low as 78. So I'm going to say maybe 90 kilojoules per mole for the base catalyzed mechanism. So it's just a reasonable estimate. And I put that right here. So here's my activation energies. Okay, let's move them down here so that we have them right where we need them. Okay. So that means that my K neutral at T2 is what I need to calculate here. So let's see. ln of K2 over K1 is equal to the activation energy. Oh, and let's put R here. Since this is in kilojoules per mole, I want my R to be in kilojoules per mole Kelvin. And of course, my T1 is 25 C. And so in Kelvin, that is that plus 273.15. Always good to have lots of decimal places for that sort of thing. Okay, and my T2 is now 5 degrees Celsius, which is 278 degrees Kelvin. Okay, so, and just for good measure, I will do 1 over equals, 1 over that. Just makes my formulas a little bit easier when I get around to doing them. Okay, so here's my natural log of K2 over K1, and that's going to be equal to the activation energy. We're doing the neutral here, so that's that, divided by R, which is there, times 1 over T1 minus 1 over T2. Booyah, okay. So now if I just want K2 over K1, that, because this was natural log, so now I take the EXP of this. Okay, so what that's telling me is that K2 is dropped to only 4% of what it was at 25 degrees Celsius. And that makes some sense because these are big activation energies. These chemical processors are very, very temperature dependent. So if that's K2 over K1, then K2 is that, equals that times K1, which is up here. Here's my neutral at K at temperature 1. And again, same units, 1 over seconds. All right, so there's my K. I should be careful to call this Kn at T2. So that's important. Let's make that yellow. Okay, now let's do KB at T2. So same kind of thing here. I'm just going to copy these. All right, so that is equal to, let's see, now my base catalyzed activation energy divided by R times, again, T1, 1 over T1 minus 1 over T2. Okay, not quite as negative, which means that the difference between the two is not quite as big. EXP of that. So now it's 7%. So it's gone down. I mean, the point here is that in both cases, the rate constant's gone down. Remember when we were talking about equilibrium constants and we were like, I don't know, sometimes they go up, sometimes they go down with temperature. I don't know. Rate constants always get slower as the temperature goes down. Period. Full stop. Always. All right. So that means that K2, and so this is KB at T2 is equal to that times the KB at temperature 1, which is here. And this is 1 over molar second. Okay, and now we want to back out the pseudo first order, but our hydroxide concentration is now different, right? Our pH is now 7.5, which means that our proton concentration is 10 to the minus that. There we go, and that's in molar. So our OH, H is let's see, it would be, I always forget how to do this. I get it backwards. It would be, okay. The other thing is our dissociation constant is different at 5 degrees. And I looked this up from a table somewhere. Okay, so our dissociation constant is different. So here's our dissociation constant divided by the hydroxide or the proton concentration. So now it's slightly different. Okay, but still notice, so here's 5.7 times 10 to the minus 8, and up here it was, where was it? 3 times 10 to the minus 8. So it has changed. Not as much as you might think, because, you know, we're using a different acid dissociation constant at a different temperature. Anyway, okay, so K prime B at T2 is now that times that, and now we're in 1/seconds. So now I'm going to copy this whole thing from up here. Just make sure that we get this right. So this is now Kn at T2 is here, and Kb is here. And so now much longer. Much longer, right? About an order of magnitude longer, because we went down our remember right here, we went down by 7%. We're down to 7% of what we had before. If we were going down to 10%, it would be exactly 1 order of magnitude slower. It's a little bit more than that. So much slower. We could even do this in terms of years. Divided by 365.25. Don't forget the leap years. So yeah, we went, so first of all, we went from, too many, okay, there we go. We went from, I'll do the same thing here, put this in years. We went from 12 years to 1 year, actually a little bit less than 1 year, 0.7 years hydrolysis. And this was at a more basic pH, right? The pH was 8.5, which is more basic. There's more hydroxide around. So both the temperature and the amount of hydroxide were causing the reaction to go faster. So that's why things are faster here. Both of those factors are working against you when you get down to the hypolimnion, and the half-life is much longer. Okay. The other thing you notice is that the base catalyzed mechanism was faster here, but now the base catalyzed mechanism is actually slower because there's less base around, there's less hydroxide. Even though we said it had a smaller activation energy, which means that the slowdown was not quite as much, but that slowdown is coupled with the fact that you have less base around. So now the base catalyzed mechanism is actually slower. So the mechanism that dominated flipped between the epilimnion and the hypolimnion, and the half-lives are much slower in the hypolimnion. Now this should be true for your chemical as well, because we just said, remember, all processes, all chemical reactions that have an activation energy will get slower at lower temperatures. So your half-lives should definitely go up when you go down to the hypolimnion. And also, again, we have a more acidic pH, so there's less hydroxide around, so the base catalyzed mechanism should get a lot slower. Okay, so that's how to do homework number 12.